Hi, today I'll be talking about Mantis, a framework for implementing expressive and fine-grained reactive behaviors on top of today's programmable switches. This is a joint work with John Sonchak and Vincent Liu. In today's data center networks, a common task is to react to current network conditions. Examples of this type of behaviors include detecting failures and then rerouting around them, identifying malicious flows and then filtering based on the security policies, and recognizing load imbalance and then adjusting the traffic distribution. All of these share the same structure, measuring current network conditions and then updating the network devices' behaviors to match them. In data centers, these reactions need to be fast, often sub-RTT level. Today, there are a few ways to implement these type of reactive behaviors. Traditionally, one could leverage the control plane, for example, SDNs or conventional control loops. These approaches are flexible, but typically they are slow and often orders of magnitude slower to capture the transient network events. The other general approach is to directly integrate reactions into the data plane hardware. These are fast, but limited by the current hardware capabilities. Now, you might think programmable switches don't fit into this category because they are reconfigurable. Yet unfortunately, there's still a well-known set of limitations. For example, these constraints include limited operations and branching allowed in actions, unavailability to manipulate match action table entries from the data plane, and so on. Over the years, previous work has come up several workarounds, but these workarounds have drawbacks. For example, one could leverage recirculation to achieve Turing completeness, but it could significantly degrade the usable throughput of the switch. In the end, these workarounds are non-trivial to design and often consume extensive switch resources, even if they are possible. In this work, we explore the question, can we enable in-network reactions to both capture microseconds level events and provide utmost flexibility? Our approach is to push the reaction loop as close to the switch ASIC as possible. Meanwhile, co-design the data plane program for fine-grained malleability and ease of use. Hence, we present Mantis. At the center of Mantis is a reaction loop, where the Mantis control plane pulls measurement and updates portions of the data plane at a granularity of tens of microseconds. The reaction logic of the control plane can be arbitrary C code. Specifying this behavior is the P4R language, a simple extension to P4 that enables users to specify which portions of P4 program should be malleable and to define the reaction logic. The Mantis compiler then transforms the P4R code into deployable codes, ensuring runtime reconfiguration and serializability of the reaction loop. There are two core abstractions underlying Mantis: malleable entities and reaction. For the rest of the presentation, we'll walk through each component of Mantis by taking a top-down approach. First, I will introduce how to express reactive behaviors with P4R using a concrete example. Let's start with a simple P4 code snippet. Here's the action and table that, based on the destination addresses, assigns the priority levels. What if we want to reconfigure this priority based on the queue depths? First, we declare a malleable entity, for example, a malleable value that takes 16-bit value and gets initialized to 1. Next, we replace the constant value with reference to the defined malleable value. Finally, we define the reaction function that specifies the data plane matrix to pull, the arbitrary C code to compute the control logic on a general purpose CPU, and the reconfiguration of the malleable entities with a simple syntax. The above is just a simple example. It turns out that besides malleable values, one could also dynamically reconfigure other P4 objects, such as fields and tables. Meanwhile, besides register arguments, one could also specify other data plane objects, such as header or metadata fields, malleable fields and use them as if they were C variables or arrays. Now, I'm going to talk about how to translate P4R into something deployable in RMT switches. One of the primary goals of Mantis translation is to create a P4 program that is dynamically reconfigurable, that is, without interrupting the data plane and losing states. Again, let's look at the previous example. To accomplish this, first, Mantis replaces the malleable value P4R with a concrete P4 object called P4R meta. Then, it instantiates a P4R init table at the beginning of each packet processing pipeline with actions to set its value. Configuring this way means that by changing a single table entry, specifically of the P4R init table, Mantis can reconfigure all uses of a malleable value in the entire pipeline. This is just a simple example. Transformation of other malleable entities requires further steps, with more details in the paper. Now, we have seen how to translate a simple P4R program with a single operation. I'm going to talk about more complex operations and the concurrency issues that result. To see why concurrency potentially causes issues, consider a reaction function that pulls the source and destination addresses of a packet. A user might reasonably expect that the source and destination addresses in a single iteration of a reaction function will come from the same packet P1. However, without coordination, what could happen is that during the first poll, it gets the value of source from packet thread P1, but then during the second poll, it gets the value of destination from another packet P2. Such non-isolated measurement could break the semantics of the reaction logic. Similar problems arise when updating multiple entities in the same reaction. To address the issue, Mantis provides per pipeline, per reaction serializable isolation between measurements, updates, and packet processing. Note that the isolation I'm talking about here is the isolation of ACID, which is to say that all three types of transactions appear to execute in some sequential order, though in fact they are concurrent. This makes it easier to reason about the reactive behaviors. The concrete approach to ensure isolation are in the extended video and paper. Finally, let's talk about the Mantis control plane. Mantis control plane runs on switches on both CPUs. Modern data center switches already use this CPU for tasks such as routing and configuration. However, these interactions are traditionally assumed to be on a slow path. Instead, Mantis control plane is reaction-centric, designed for repeated reads and writes to the switching ASIC. It splits operations into a prologue phase and dialog phase, where the prologue precomputes as much as it can and the dialog implements the reaction. This design, along with aggressive optimizations, allow Mantis to execute the reaction at granularities that are on the same order of magnitude as the PCIe latency of the underlying system. We implemented a Mantis prototype that runs on a Tofino switch. When evaluating Mantis, we found that Mantis achieves fast reaction time of tens of microseconds. Besides, Mantis renders low data plane and CPU overhead and supports a wide range of sub-RTD applications. More details are in the extended video and paper. To summarize, Mantis introduces fine-grained reaction to network statistics as first-class citizen. Mantis provides a simple to reason about set of reaction abstractions with P4R interface, and enables a wide range of sub-RTD reactive behaviors without penalizing the line rate packet processing speed. Thank you so much for your attention.
Thank you for a really cool system and a great talk. I just wanted to point out one thing that I neglected to mention when introducing this paper, as well as the first paper in this session, Netlock. Make that mistake twice. Both of these papers were submitted to the artifact evaluation and actually received all 3 badges available. The results were reproducible and also reusable by others, which is great. And so you can check this out on GitHub. I also love that the GitHub organization is ENIAC. That's the name of the early computer that was built at Penn. Super cool. So one question from the Q&A already. What are the trade-offs for using Mantis, in particular with respect to pipeline resources Can you say a bit about how much extra it costs to use the system?
Okay, thank you for your question. Yeah, it's a detailed and great question. So I guess I'll answer the second sub-question first. So yeah, it's true that we have P4R init table at the beginning of the pipeline. However, it doesn't necessarily like add to an extra stage because the pipeline, the compiler underneath will basically the Tofino compiler will analyze the dependencies, and only if like the like following tables that depends on that configuration will be allocated to the like the stages afterwards. So, but it's true that's an extra table cost for that. And for the other trade-offs, probably one cost that Mantis adds is like it adds an extra busy core at the CPU. However, that could be traded, which is shown in our extended video and paper as well. And for other memory costs, for example, at the data plane, it's generally it's low, but we found that probably the most expensive one is to use the multiple fill, as we mentioned in the table. However, it still scales linearly with respect to the number of usage. Yeah, hope that answered the question. Thank you.
Great. So another question, just long-term about the language. I see you have some language extensions to P4. Are you planning to contribute these to the P4 spec, or do you view P4R as its own dialect that will live on independently of the language?
So the question is, are we planning to extend it to P4? We haven't actually take that step, to be honest. But it is like, we believe that it's a nice extension when the user or programmer wants to actually implement the reactive behavior on top of it.
So another question from Inan Chai from Alibaba. Interesting work, and is curious about scalability, not from a pipeline or performance situation, but from the programmer's perspective. So have you done any studies to look at how much code you would write without Mantis, and then how much you write with Mantis using your compiler to generate the implementation?
Great question. So actually, in the paper, we have a usage table that kind of like benchmarks the lines of code that is written in P4, and then the lines of code that is written that is generated in C and P4. So certainly the amount of increase is dependent on the application. We found that it could be 2x, for example. Yeah.
Thank you for your presentation. Very interesting talk. Let me see if there's any questions. So yeah, let me ask a first question. So you say you use these malleable values as a parameter to react to the network. Could you give us some hints about who is the one that can change the malleable values in your system?
Oh, so the question is how the malleable entities are reconfigured. So the Mantis agent, so a short answer to that is the Mantis agent takes care of that. So, so basically the user specifies the malleable entities in the data plane and in the P4 code, in the P4R code, and also a reaction function that will be dynamically loaded to the Mantis agent. And then it will execute that, including the reconfiguration of the malleable entities. Yeah.
I see. So is it possible to have multiple malleable values working together to support more flexible configuration?
Yes, definitely. So that's actually one benefit of using Mantis. Yeah, because the user doesn't need to think about like the synchronized communication between the control plane and data plane, because it's actually taken care by the Mantis compiler, which generates serializable and reconfigurable code. Yeah, hope that answers.
So now you have these malleable values. Have you thought about if there are different applications they want to modify the value at the same time, will be there some conflict issues between different applications wanting to modify the values simultaneously?
So you're saying does it exist some application
No, this malleable value can be reconfigured, right?
Yes.
So there might be multiple applications or multiple different flows. They want to modify these values maybe at the same time. Is it possible that they will conflict with each other and destroy the system?
Yeah, thank you for the question. So that comes like when you have multiple operations at the same time, and what Mantis provides is a serializable isolation. For that, it provides the expectation for the user that they are executing in some sequential order. So so that makes it easier to reason about the reactive behavior. Yeah, so that could address the issue. Yeah.
Okay, good. And so finally, could you give us some applications that may benefit from your system?
Oh, sure. So actually in the paper, we have several example use cases, such as failover and security applications. So yeah, with more details actually in the paper.
Okay. So the final question, someone is asking, the commodity switch typically uses very weak CPU. So what is the CPU usage in your experiments?
That's a great question. Yes. So currently, so if you to achieve like almost CPU utmost latency, I mean optimize the latency. The CPU cost for that is 1 basic core. But however, that could be traded, and even in that case, we could achieve like 50 microseconds for like 20% of usage. Yeah.